In this video, we'll look at deletion from red-black tree. This is a little complex topic, but I will make it very simple. This is similar to deletion from binary search tree and involving rotations or recoloring of nodes. So let us look at the method for deletion from binary search tree. So first of all, understand it perfectly. Then deletion from red-black tree is very easy. So let us understand. So already I have taken an example. This is a red-black tree, but don't see it as a red-black tree. Look at it as a binary search tree. Now, how deletion happens in binary search tree? As an example, let us delete some nodes and see the cases. So in this, whatever we understand here, that will help us understanding deletion from red-black tree. So focus on this procedure for deletion from binary search tree. Let us take example. Suppose I want to delete 90. So the method for deletion from binary search tree is first of all search for 90. 90 is greater, this is greater than this, greater than this. Yes, it is found. So we delete it. This is a leaf node. So we have to simply delete it. Now next, second example. I want to delete 20. Search for 20. 20 is less than this one. Yes, it is found. Then we delete this node. Actually in binary search tree, we don't delete that node. We delete the value. Then that node is kept as it is. Some other value will take its place. Who will take the place? Either in order predecessor or in order successor. So who comes before this node in order traversal? This one. And who comes after this one? 30. So either 10 will take its place or 30 will take its place. Alright. Now you can observe one thing. The node that is deleted is 30 and that is a leaf node. So 30 will come here and this node we will delete physically. 30 is a leaf node. So one thing we can understand that whenever you delete some from binary search tree, a leaf node is deleted. Then next, I said 10 will be deleted. 10 is not a leaf node, but it is having only one child. It is not having right child. It is having left child. Yes. So when you are deleting a node from a binary search tree, either it may be a leaf node or it will have exactly one child. It will not have two children. This is the very important point. Now let us observe through some more examples. Suppose I want to delete 50. Who will take its place? First of all, we'll remove 50. 50 is the first value found. So remove 50 and its place we will bring some other node and we will delete that node. So who will come here? In order predecessor. Who is in order predecessor? Which comes before 50? 40 comes before 50. Right? Or else in order successor, who will come after 50? 60 will come. So either 40 will go in its place or 60 will go its place. So 40 goes their place and we will delete 40, or 60 go to its place and we will delete 60. Now if you observe in this example, 60 is a leaf node, right? And 40 is not a leaf node. It is having one child, that is left child. It will not have right child. If suppose there is one child here, there is one child here, right? What it could be, it is greater than 40. So let us say 45. Then if I delete 50, who will take its place? 40 will not take its place. 45 will take its place. So that's what. So this will not be there. So when 40 is taking place means it is having left child. So finally we can say that when we are deleting from binary search tree, it will be a leaf node or it will have exactly one child. Remember this thing. Now the deletion from red-black tree depends on this only. So in red-black tree, deletion have many cases. If you refer to textbooks, some authors say there are 6 cases, some authors say there are 8 cases. I will say there are no cases. Though I have written some cases here, but don't see it as cases. Now based on the deletion procedure from binary search tree, we will try to delete from red-black tree. Now let us come to the examples. Before that, see once again, remember this, we will be working at the leaf level, that is the last level of a tree, right? We will not be working towards the root, we will be working towards leaf because this node goes there and this nodes we have to adjust. So that's why I have these examples, right? So we are working on the smaller level, right? Lowest level. Now let us see. Suppose for example, this is a red-black tree. Imagine there are other nodes are also there. Now from this, I want to delete. Which node I want to delete? This node. Whatever the value is there in that one, I want to delete that node. Then search for the key, node is found, delete it. And you don't have to do anything because it is a red node and it is not having any children. So this is the first thing. So whenever you are deleting anything from red black tree and that node is red, simply delete it. You don't have to do anything. Let us see. I want to delete 30. Search for 30. 30 is found. 30 is red. Delete it. I want to delete 75. Search for 75. 75 is found. Delete it. Don't do anything. You don't have to do any changes in the red black tree. Just delete that node. Now one more example. I want to delete 70. Who will take its place? Either in order predecessor or in order successor. Either 60 will take its place or 75 will take its place. Suppose if you are sending 75 there, then you have to delete this node. So what is the color of this node? Red. Delete it. Simply delete it. 75 goes there and you don't have to do anything. Don't have to do any adjustment at all. Okay. So if the node that you are deleting is red, then blindly delete that node. Now let us look at another example. Same thing, red node. Suppose I want to delete this node, red node, then simply delete it. It's a red node. I have shown it here. Now I am showing it on this side, right? So delete it is this one. Now next one. I want to delete the node. Suppose I have to delete this node and it is having one child. It is having just one child, and that child definitely it will be black because red color node will not have red color child. It will have black color. So this is black color. So if this node is deleted, red color is going away, then simply bring this node here and it becomes black node, right? This node is gone. This node is gone. See, remember, this was having only one left child, right? Right child was not there. Only one child was there. So if you are deleting a node that is a red node, then it will simply delete and its child will take its place if there is any child. And definitely that child will be black child. So from these three examples, we can understand that if there is a red node, then search it for it, and it is red, then delete it. There are no issues. Then where is the issue? If the node is black, then there is a problem. Now we are coming to the actual complex part of red black tree. Let us make it simple and understand it. Let us see. I have another example here. So for deletion, we considered some nodes. Let us see. This is the node that is getting deleted. So I wrote it as a D, and it is having, suppose, child. Okay, this is the child, and this is the parent, and this is sibling of a node that is getting deleted. Sibling of a node that is getting deleted. Now, when the node that you are deleting is black, there is a complexity, and it's not that complex. Let us understand it. Suppose I want to delete a node that is black, right? Then check the sibling. Sibling is red. Then simply delete this node, delete the node, and perform rotation. Perform rotation. So here comes S and here comes P, and this child is red. So that became black and its two children became red. Perform rotation. That's all. It's simple. So what was the situation here? The node that we are deleting is black, right? And its child will take its place. Then after that, its sibling is red. So perform rotation. It's simple. So which rotation we perform? We have performed zig-zag rotation. That is RR rotation. If it was this side, we'll perform LL rotation. Okay, this is simple. This is simple. Now comes the complex cases, complex part. See this. The node we are deleting is black, right? And it is having some child, black child. That is null. And its sibling is black. See, if it was red, perform rotation, no problem. If it is black, then we have multiple choices here. What are those? We have two choices. What is that? If both the children are black, then simply change the color. So how to change the color? Sibling, you make it as red, and let these children be black only, and make the parent as black, right? And its deleted node, this has came here. That node has gone, and its child, that is null, has came here. This is how change the colors. Sibling is black and its children are also black. So do recoloring. Change sibling to red and parent as black. Now parent was already red, so it became black, so there is no issue. Otherwise, this will continue in the parent. So that recoloring part or rotation part will continue. We don't have to go to that much complexity. So that's it. Now, one more possibility in this one. See, the node that we are deleting is this one, and it is having null, nothing is there on this side, okay? This node we are deleting, and it is black, and its sibling is also black. Yes, then what are its children? If it is having one child or two children, whatever it is having, if they are red, they are not black, then again perform rotation. Again perform rotation. So I have taken left red child. So which rotation we have to perform? Zigzag rotation we have to perform. That is, this red goes up and the parent comes here, that is red, and sibling comes here, that is black. Sorry, parent and sibling are black and that red goes there. So this is how you have to perform the rotation. Zigzag rotation. If it is having right child, then zigzag rotation. If both the children, you have both the option, so better perform zigzag rotation, that is RR rotation. Now which rotation is performed, it depends on the which child is available, right? If for this node, if left child is there, perform zigzag. If right child is there, zigzag. If both are there, then also zigzag. So again, if you break them, these are cases again. These are cases. So I'm not breaking them. Now, one more thing. There is something called blackness, double blackness. What is that? I did not explain anything, right? I will come to it. Now let us repeat the topic again and see all the things quickly. Let us see. If I am deleting a node that is red color node, then delete it simply. Don't do anything. If I am deleting a node that is red color node, then delete it simply. Don't do anything. If I am deleting a node that is red color node and it was having a black child, then also delete it and its black child will take its place. There was no problem. Why there was no problem? Because in red black tree, the number of black nodes along any path should be same. So if you are deleting a red color node, it's not going to affect red black tree at all. That property is not affected at all. So that is the reason, if the node is red, then simply delete it. So we are bothered about the number of black nodes along every path, that is black height. We are bothered about that. And the problem is when the node is black. So that's how, if the node that you are deleting is black, then there are other situations. What are the situations? If a node is black, then if this is deleted, then this is already null is black. So null comes here, right? And that node that was deleted, it was black, so black height is reduced in this direction for one time. So we make this node as, say, double black. It is having more blackness. That was null, that is its own blackness, and the node that is deleted, that blackness also. So we have to adjust that blackness. So we have to adjust black height. So that is a problem here. If the node that you are deleting is black, then it will become double black, right? Its child will become double black. Then what are the possibilities and how to handle? So for when it is double black, see that sibling. If it is red, perform rotation. Next, I'll directly jump here. If the node is deleted, then this was null. See, it will be null only definitely because the nodes are leaf nodes. The nodes that are deleted are leaf nodes. Remember this. Sibling is red, definitely children will be black. Rotation. Sibling is black, children are red. Rotation. Then another case. Sibling is black, children are also black, then recolor. So simple. Let us do it more simple once again. If the node is red, delete it. Node is red, delete it. Node is red and the child is black, definitely will be black, it will take its place. So node is red, delete it. If the node is black, then it will become double black. Then see the sibling. If it is red, rotate. If it is black and children are red, rotate. If it is black, children are also black, recolor. So this is the procedure. So if you want to break, you can break it into many cases, right? This case, second case, third case, fourth case, fifth, and again this is sixth and seventh. You can have many cases. So I have not shown them in the form of a cases. I said that the node that you are deleting is red or black. That's all. So these are the ways how nodes can be adjusted after deleting from red black tree. Now I will take a example of red black tree and delete few nodes from it. In the next video you can watch it. So let us take a red black tree and delete some nodes from it.